Ben has been a really good friend over decades, and I have him to blame actually for writing a paper called The Case for Humans on Mars. And we used that when we put together the first Case for Mars conference. We stole his title, but we took out the man part because Carol Stoker put her foot down. Anyway, Ben is a former chief scientist of space exploration systems at Lockheed Martin in Denver. He's designed the instrument for the Viking Mars missions that discovered sulfate salt and high iron in Martian soil. He is one of only a few scientists who have been on the Mars science teams for the Viking missions, Phoenix mission, the Phoenix lander mission, and the rovers named Spirit and Opportunity, as well as Curiosity and now Perseverance. So he's a committed Martian for decades and decades, and one of the people I turn to when I always get into a corner and I can't figure what just happened. So with that, Ben Clark.
Yeah, and okay. Ben, maybe you can introduce Vera too. And I know you're going to say a few words about your the book you wrote together, right?
Yeah, so this is Vera, my fiance, and we. Oh, good. You're showing it.
Yeah, your fiance. Yeah.
Well, I would just like to say a few words about our book that Ben and I co-authored, and it is titled Astrobiology for a General Reader. Here it is on the screen, and it is a questions and answers approach. So it is very easy to read. It is available on Amazon or from the publisher, which is Cambridge Scholar Publishing. But whoever wants to buy it, I suggest you wait until price comes down. And since before I let Ben talk about important things, since you heard my voice and you think I'm linguistically challenged, I am well suited for this Mars mission because I know how to pronounce Jezero Lake. It is not Jezero, it is Jezero, because this is my home country, so I know how to pronounce it. Nobody will do it, but that is not it. It is Jezero Lake, and here comes Jezero, I'm sorry, means lake, okay, in Serbo-Croatian. So, okay, sorry, here comes Ben.
Okay, I'm going to try to share. The screen. Is that showing up?
Yeah.
Presentation?
Got it.
Yeah.
It's there.
Okay.
You might want to take off the left side.
Yeah, can you go full?
Yeah, there
we go. Great.
Okay.
He was
and so I'll say at the beginning that the missions you just described, the Perseverance and also actually the Curiosity mission before that, the rockets that launched those were Atlas rockets built by Lockheed Martin, and also the aeroshells that you showed was the entry. Those were all built here in Denver by Lockheed Martin. And we also, it turns out on this upcoming mission, the little helicopter was built by JPL, but they asked Lockheed Martin to build all the housing and the deployment system for the rover, for the helicopter when it comes out of the rover. So that'll be coming up. So this is what the Perseverance rover looks like. And this, of course, is just an artist's impression, but it'll be taking self-portrait pictures eventually, so you'll get pictures of it on Mars. This is what it looks like in full mock-up, and so you can see it's just about big enough for a person to write on. Really good. which is one reason it's so expensive. This is a lineup of the instruments on board, and you can get this on Wikipedia, or also you're going to get the web link to the JPL place that describes the rover in a lot of detail. The instrument that I work on is called Pixel, which is one of the two science instruments mounted on the arm. So we'll be able to tell you the chemistry of rocks and soil and sediments when they put our instrument next to those and allow us to take data. Now this is the Jezero, and at one time it was a lake. And we know this because you can see a river flowing into it on the left and another river flowing out of it on the far right side. And because these two rivers are at different elevations, we know that at one time it had about roughly a mile deep at the deepest point worth of water in it. So it was that was back in the time when Mars was much warmer and much wetter. Today it's more ice and it's drier because it's colder. The X is where we landed. We purposely landed close to the inlet river. And this is kind of what it looks like. The X is where we landed, kind of in between these. There's a couple of craters here. I'll use my cursor and see if you can see the cursor. Mark these two craters. So they kind of form a triangle. This path is what we may use to drive, but this is something was planned a long time ago as a straw man. And the one thing is to go by this crater and examine it, and then go look at the delta itself. This is the material, like the Mississippi River does when it goes into the Gulf of Mexico, forms this delta with a lot of debris that's washed down the river. And very, very interested in that. It samples lots of lime. Go over to this little mountain and so forth. It's going to take a couple of years to get this distance, mainly because we'll be stopped most of the time between sampling and taking samples to return to Earth. And this is color rendition. This is not the true color. This is the way geologists make little cartoons to show things. So here's where we landed. Here's those two craters, and here's the delta. And you see this big crater here, but if you look closer, there's lots of craters here. And that's true for Mars in general. Mars is just loaded with craters. There's about 10,000 craters on Mars that are larger than, that'd be about 6 miles across. So each one of them is big enough to cover a city on Earth. 10,000 of them. And these craters are big enough to create a lot of heat when they hit. So they'll melt any ice that's in the ground and form a little hot lake while they're there. And they also kick material up away from the planet. That's the basis of the idea that I'm going to talk about. So we have, in addition to craters, we have riverbeds on Mars. They're empty now, but there was a lot of water flowing at one time, as well as lakes. So the question I raised is, are we ourselves actually from Mars? So the hypothesis is that life arose on Mars. It was transported to Earth in meteorites, and then it took root here and took over. In the meantime, Mars became cold and dry, and so it didn't flourish there. So why in the world would we believe something like that? It's purely a hypothesis. But the point is that it's actually possible. For a variety of reasons, it's even somewhat probable, but we won't know until we discover life on Mars. Then we can compare the two life forms, and then we'll know for sure one way or the other. So what happened was, when we have an impact on Mars, it's when an asteroid or a comet hits Mars, it will kick material. So the blue circle is the Earth in orbit around the sun. The red circle is Mars in orbit around the sun. And when you hit Mars with a large object, these are going extremely fast, thousands of miles an hour when they hit. It'll kick material up off the planet, and they'll go into orbit like this white dotted orbit. And you see that orbit crosses the orbit of the Earth. So when Earth moves to a point such that both the meteorite and the Earth are at the same location, it will enter the Earth's atmosphere and land on the ground. So we have We now have 200 or 300 of meteorites that we know are from Mars. We only know that because we've been to Mars, so we know what the Mars composition is accurately enough that we can tell these are from Mars. And you can see these meteorites have a black coating on the outside. That's because as the rock enters the Earth, going thousands of miles an hour, it essentially melts thin crust on the meteorite. So if you find a rock on the ground somewhere that looks something like this with black material on the surface, hold on to that because it's probably a meteorite. So life on Mars assumes many, many different forms. Bacteria, all the way up to dinosaurs. Huge difference. If we find a dinosaur bone on Mars, that's going to be an easy way to detect life. But we doubt that dinosaurs ever reigned on Mars. The bacteria almost certainly did. The first several billion years of life on Earth was basically just bacteria. And then they eventually evolved into all these other creatures. So Mars is a dry, cold desert. We keep hoping for something exciting to happen. When we landed with Viking, you know, people made their jokes like Leonard was saying, this really is an old Viking slide. And some people said, well, you know, it looks pretty lifeless, but what if we just can't see what's really there? And it's true, there's no way our cameras could see bacteria. And in fact, none of the missions have cameras strong enough or microscopes strong enough to see bacteria. So we have to try and detect them chemically or otherwise. So the new missions have showed that unlike Viking, it's not just dirt and rock, it's a lot of sediments. And so all these striated things are sediments laid down when this was originally a lake. This is the Gale crater, which is the Curiosity mission. It's been operating for more than a half dozen years now. So we have to kind of go back and ask, well, how did life arise and could it arise on Mars? So nobody knows for sure. There's a lot of ideas out there involving volcanoes and other things. So I'll give a little summary. One thing that scientists now agree on pretty strongly is that the original life on Mars was probably RNA. And RNA is a molecule on the right. DNA, which we all heard a lot about, is on the left. DNA and RNA are similar, but RNA is much more versatile. And in fact, unfortunately, this COVID virus that is attacking us is an RNA type virus, very, very sophisticated one. It's able to go into cells and reprogram them and make more virus. But the way we're attacking it with the new vaccines is with a different kind of virus that we have designed to get our immune system to develop the capabilities to recognize the COVID virus and kill it. So RNA is extremely versatile. We think that's how life started, and eventually DNA formed and proteins formed. So in order to do that, you need certain ingredients. You need water. All life needs water. You need organic molecules. We're not talking about what's called organic food at the grocery store. We're talking basically about all food. And in fact, Vera is an organic chemist, and that's what she taught for 31 years in university. You also need certain elements that are not organic, and then you need a dynamic environment because some of the reactions that need to occur to form proteins and DNA and RNA require that you dry them, the chemicals out, and then re-wet them again, and you go through that a few times. So there's quite a few different really outstanding scientists that have worked on this problem of how do you go from organic chemistry to life. And Vera is one of them who worked with some of these key people on the slide here. Miller Orgel at the very bottom. She worked with Miller and Orgel, both very famous, both deceased now, but very, very top-notch. And all these theories seem to have one particular thing in common, although different, but they have something in common, and that's sulfur. And so what I want to point out is that when we first landed on Mars with Viking, one of the most important things we discovered was the soil was loaded with sulfur. Sulfur in the form of sulfate which is a salt. And it's about 100 times richer in sulfur than the Earth is. So it's already got a head start on the origin of life because it's got the sulfur that all these different theories each want to have in how the chemistry is developed. And here's an example on Mars. These are rover tracks that dug this up. We almost got stuck here, but beneath the red surface, there was this deep bed of really highly concentrated iron sulfate. And so it's sulfur's just all over Mars. So here's one of the top researchers these days on how life may have started. And they came up with a system that has very few chemicals in it, but can produce RNA, can produce proteins, and can produce lipids. Lipids are the things that make the cell membranes that enclose your cells. And so these are the key ingredients to make a cell. But they do it with a very few ingredients. They start with cyanide, which we think was present on early Earth and early Mars, and then some sulfur compounds. Ultraviolet light, had a lot of ultraviolet back in those days. Plus it turned out they needed some copper, some iron, and some phosphorus. Now, part of the problem is to do these reactions to make proteins and DNA separately, you have to do it in different test tubes because you have to use somewhat different conditions. You have the same starting ingredients, but you change the conditions, you get a different result. We don't have test tubes on Mars or Earth when we started life. So how do you do that? Well, the idea is that you have small areas that are able to sequester the different things. And so on one of the earliest ideas of where life started was just in a pond. Darwin himself, when he was discovering how life evolved, hypothesized that maybe life started in a little pond, a warm little pond. And you'll notice here, these ponds have dry areas, and these are mud cracks. So the water comes and goes depending on rainfall. And so you get wet and dry cycles that convert these chemicals into things like RNA and proteins. Another idea is that all these impactors could form lakes. Yet another idea is on volcanoes, around volcanic areas, or just the areas where there's lava near the surface, you get hot springs. And these are kind of similar to the warm little pond, but they produce even more minerals. And then there's another area under the oceans, deep under the ocean, where you have water that's gone down into the ground and gotten heated by lava that's underground. And then it extracts a lot of minerals, it makes these chimneys as it comes out. And these are called hydrothermal vents. So lots of different ideas. Here's the idea we like most, which is the little pond, warm little pond. And we wrote a paper last year that described how they have different parts of this pond doing different things chemically on the shorelines. You can also have things happening at the bottom. Some of these chemicals sink and others float and others are dissolved in the water. So you get a lot of different things and you can get wet, dry. But each different scenario has different ways of doing it. So nobody knows for sure how life started. Maybe more than one way, maybe two or three. So one of the things we discovered with Curiosity is we found some fossilized mud cracks. This is the best example so far, but it proves that we did have warm little ponds with wet and dry cycling on Mars. So this was a big breakthrough. We were in Yellowstone, what was it, a year and a half ago? Yeah, about a year and a half ago. And this was kind of an ideal little area you can see where you have water, hot water with all these chemicals in it. You have a dry area, so you're having both wet and dry happening next to each other. You have streams that overlap each other, so different little ponds can have different chemistries, then they can all combine down in these areas down here. So we think that's a good example of what may have happened. This is in Russia, Kamchatka. Vera's been corresponding with one of the scientists that does exploration there. And it's also an area where you have a lot of hot springs next to volcanoes. And you can see in the middle where there's no green, that's all chemicals. And these are chemicals that could be undergoing reactions leading to life. So on Mars, we discovered something we called home plate because it kind of looked like that from high up. This is a picture from orbit. You can see the little Spirit rover. And in fact, this is where Spirit died. It's where it got stuck and then it froze to death after, what was it? I think about 6 years, maybe. Anyway, this home plate, we think, was one of those hot spring areas on Mars based on the chemistry. A lot of sulfur and iron in this area. So Mars was warm and wet. We know that. Did it have all the right ingredients? Well, I'm going to show a few slides. We'll go pretty fast with these because it's chemistry, but there's no equations. Not going to teach a course like Vera did, so you won't have any exams.
Or quizzes.
Or pop quizzes. So the most essential elements are these. These are the ones that make up the organic molecules in the surface. So you have carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. So to make proteins at the top, you need all of these except phosphorus. And to make DNA and RNA, you need all of these except sulfur. You need the phosphorus down below and sulfur above. So without these 5 elements, you cannot make life as we understand it. Well, we discovered mostly with Viking and later augmented some, these elements were all available on Mars. Some of them were in the atmosphere. That's the ones on top here in blue. And some were in the soil. And you can see some of the elements are more in one place. So there were plenty of necessary elements to go around. But it's even more complicated than this. There's more elements than just these 6 elements that you need to be alive. You don't have to go very far to find it. Just take your multivitamin bottle that has minerals and look on the back, and it'll give you a list. And so these are some of these key elements. Copper, iron is Fe, phosphorus, zinc, calcium, chromium, magnesium, and manganese. And I can tell you that all of these elements we're discovering in almost every sample we analyze on Mars, exception of copper, but we're finding copper enriched in about every 1 out of 10 samples. So all of these elements are present on Mars and pretty much in spades. I'll give you a few examples. This is what, scientists don't use vitamin bottles to write their papers. So this is the way we present the data. This is a periodic table showing the elements that are essential for life. And here's an example of some of these key elements. Nickel on Mars, the red bar, is compared to the blue little bar down here. Blue is the average nickel concentration on Earth. The yellow is the average concentration on Mars, much higher, but we've seen concentrations as high as the red bar on Mars. Same thing for copper, much more copper on these special locations on Mars. And zinc is extremely prevalent on Mars compared to Earth. And it's very high in the soil as well compared to Earth. So these elements are in abundance on Mars. And it seemed like Mars might be more ideal than Earth to start life. Here's a picture of manganese on this rock. This rock was flipped over by the wheel accidentally, and it had this coating of manganese underneath. And some more manganese over here in a wheel crater, completely different location on Mars. These are calcium sulfate veins, and in these veins, we detected boron, and boron is one of the elements that is also thought necessary to start life. Not so essential for us to eat, but it was necessary, we think, to make RNA. And boron Mars can be up to 300 parts per million so far. We'll probably discover even more eventually. Only 10 parts per million in the Earth's crust. You have to go to Death Valley to find borax. So again, the premise was life arose on Mars and that came to Earth and became fun. Now, one of the reasons that we think this might be particularly appropriate is that the Earth at the beginning of history, back when it was formed, acquired a large ocean, and so large that we think the Earth may have been totally covered There weren't any continents. Now, this is an actual space photograph. This is not an artist's conception. This is a picture taken from space of the Pacific Ocean. And so it's, you know, ignores the continent. They're on the other side. But it turns out that continents on Earth, this is on the left, is when the Earth was formed, and Mars at the same time. And as you go to the right, this is coming up in history. And about the time we think life started on Earth, there's evidence for this, the continents were just forming. You see this green line, the continents were just getting started. So the Earth was still totally water or mostly water. Whereas, and so it had a lot of water, not much sulfur, and almost no land. You see little tiny Hawaii here as an example of a volcano peaking above the water. So Mars, though, never was covered entirely by an ocean. In fact, if it had an ocean at all, this would be as large as it ever got. We do have this area on Mars is quite flat. So some people have thought at one time it was covered with water. But Mars had a very good combination of water and land throughout its entire history in the early parts when life would have started. So this is Gale Crater. And here's the various units. Currently, we're headed for this sulfate unit. We're going to be there in just a couple of weeks. And we're all extremely interested in seeing what is actually in this. We know the sulfate's there from orbit, but every time we go to these units, it turns out what we learned from orbit wasn't quite right and had to be revived. So we're all anxious to see. But that's where a lot of salts formed, and all this area was at one time underwater. It was a lake. And even after most of the water left, some water was still coming in from rivers and forming deltas like little cartoon here. So that completes the story of why some of us think that life could have started on Mars and then come to Earth before it even started on Earth. But as I said, we won't know until we find life on Mars and are able to compare the molecules. And then we have very sophisticated techniques to try and figure out what came first and when and so on. I have a few more slides. This one we already saw. And this is our landing site. This is the little helicopter. Don't get too excited about this helicopter. It's got huge blades because the atmosphere on Mars is very, very thin. So it can't carry much of the payload. The blades have to spin, I think it's like 5 times faster than normal helicopter blades. And it'll have a short range. We should get some nice picture to send back. And this will be tested out in the next 2 months. And in fact, we won't be doing science until these tests are completed. Not much anyway. We do have an instrument that's called SuperCam that can shoot lasers at rocks to get composition. And we flew it also we have it already on the Curiosity rover, but we've got an even better version on the new rover. And somebody got kind of cute and said, we should be careful what we shoot at on Mars because you never know what you'll hit. Yeah. So that's the end of my presentation.
Terrific, Ben. Thanks so much for that.
Yeah.
Let me kick off something. I've always been interested in these meteorites coming from Mars. Some people make the argument as why do we need return samples when we have meteorites already from Mars? Why do we have to go through billions of dollars to bring back? And it's almost like folklore now about what condition these meteorites on Earth are. I mean, how, in your mind, are they, subject to a lot of erosion here on Earth, or do they hold the
okay, so yeah, I'll be glad to answer that. So the meteorites that we get back on Earth, actually, some of them are in pretty good condition because we retrieve a lot of Antarctica where it's really cold and dry. So they don't get changed too much. And also you can bury into them deeper and they're protected from the environment the deeper you go in them. But the thing about them is they're all what we call igneous rocks. That means they are formed from volcanic material. They haven't been subjected much to water. Now, There's a little bit of alteration to some of them, so we find a little bit of evidence of that. But the problem is that you can't launch a rock off of Mars without essentially breaking it up into little tiny pieces unless it's very, very strong. So we're only getting the strong rock back on Earth. And those aren't the rocks we're most interested in. What we're interested in are those layered rocks. Those are sandstones and also what geologists call mudstones, which are things that have gotten kind of hard after they dry out, but they're not nearly as hard as a piece of granite, a piece of basalt. So we don't have any meteorites from Mars that are those sediments. So unfortunately, Leonard, for some reason, the answer usually given to your question is, well, we don't know where those rocks came on from Mars, and therefore we need to know where they came from, what the geologists call context. And that's a valid reason, but I don't think it's nearly as important as the reason I just discussed, which for some reason doesn't get mentioned very often. So we're really looking for rocks that could have life in them, not rocks that are from volcanoes.
Does anyone else have questions they want to ask? I think you can unmute yourself. John could unmute us all, or I don't know. I've got a question. What?
I can't unmute us all, but I can. You can unmute yourself, and please do if you have questions. Go ahead, Barb.
I have one. If we're waiting for other people, Ben, you mentioned about the dry and wet, like the pond getting dry and wet, and I imagine that's over a few years, if not thousands of years. And did you say that because of the dry and wet, the chemicals change somehow, or they recombine, or so? I don't know a lot about chemistry, so I don't know.
What that is to form a chain of molecules into a polymer to make DNA or to make proteins. Both of those are what we call polymers, long chain of chemicals. You have to get rid of some atoms so that they can hook together. And it turns out the atoms you have to get rid of are 2 hydrogen and 1 oxygen, in other words, water. And to make that reaction happen when you're wet is very tricky. Life can do it because it has enzymes that make that happen. But when you're trying to make life from scratch, you have to find some other way to do it. And the way to do that, one really good way to do that is to just dry out the sample. And then that causes these little things to hook together. And if you do it over and over, they hook longer and longer. Is that I'll let Vera chime in.
Yeah, that is correct. Yeah. What happens is if you want to remove water during the reaction, when you're running reaction in water, it's not going to happen. But if you dry the water off, which means you dry the material, then as you dry the material, the water is eliminated and you make the polymers that Ben was mentioning.
Another consequence of all this is that life probably starts pretty quickly over a matter of maybe years or, the lifetime of a pond, 100 years or something. But it doesn't take millions of years to make life. It just takes the right circumstances.
Are there other questions? I bet there are.
Why is there no rain?
That's a great question. And at one time there may have been rain because of the rivers. How do you form a river without rain? Although one idea is maybe you just had ice everywhere, it formed up and the ice melted and then it just all congealed and made rivers. But today there's no rain because you can't even make anything except very thin clouds because it's cold. So you can make these icy clouds, but they don't really melt. You just get the, as you all know from living in Colorado, when it snows, the snow doesn't always melt before it disappears. It just kind of disappears sometimes because we're so dry. And so basically the ice is evaporating, and what scientists call sublimation, but it means it's just evaporating without ever becoming liquid. And that's what Mars does today. In fact, the pressure is so low that the boiling point on Mars is about 1 degree above 0. So it can't keep water liquid right now.
Is the ice on the poles carbon dioxide or water ice?
Could you repeat that? Couldn't quite hear.
Is the ice on the poles of Mars
some
water ice or carbon dioxide ice?
Oh, that's a great question. So originally, when astronomers saw those white caps, they said, water ice.
Yeah.
When we got to Mars and made measurements, the scientists said, no, it's carbon dioxide ice. So, you know, Mars always surprises us, so that was good. But then later, as it turned out, as that pole got warmer and warmer, the carbon dioxide ice slowly disappeared. And lo and behold, underneath it was another ice cap, smaller, there was water ice. And then eventually that disappeared. Okay. So the answer to your question is yes.
Thank you.
What is her name? Judy? I think she's one of the friends.
Yeah, I have a question.
You're muted.
No, we can hear you.
Oh, okay. Yeah, I was curious how organic molecules could survive entry into the Earth's atmosphere.
Well, it's a good question. As you saw that black material on the meteorite, it's very, very hot, but the inside of the meteorite is cold. It's so cold that one of the meteorites was picked up with frost on it because the outside cooled, was found a few hours later, and the outside cooled and became frosted. There's yet another meteorite. It's actually kind of a famous one, I think, that the chemical analysis showed that a dog found it first and thought it was a fire hydrant, apparently.
What did he say? What did he say?
The dog thought it was a fire hydrant.
So any other questions? Feel free.
Hey, Ben. So that was a great presentation. Would you say that, so many scientists have been talking about Mars and, we just landed Perseverance, and is the search for life the most important thing on
You can't hear
mind?
very good. Our speaker isn't very good.
I'm sorry. I'll try to talk louder. Is finding life the most important thing that is on most scientists' mind with Perseverance right now?
Well, we can only find evidence of life. And so a lot of the interest is in finding out what the conditions were for how long on Mars, how long was it wet and warm. And so that's kind of the main thrust. But at the same time, we're looking for samples that would have more organic material in them. And so if we can find that, it might be evidence of life. We might not be able to tell ourselves, but as the mission proceeds, we're going to be taking samples, up to about 30 of them. And they'll be in little tubes. We're going to leave tubes on the ground. Then later in this decade, there'll be a mission that goes up there and picks up those samples and brings them back to
Earth. Ben, on that, those samples, I understand we may not be picking those up for 10 years.
I said decade.
Okay, so how much do you think they'll change in that time? Or do they, if they change at all, is that maybe just within the first year or even, like what could change in those?
Yeah, it's a good question. It'll actually be a little hard to tell, but they're going to be kept cold because Mars is cold. And the little capsules were designed to keep them cold as possible. So that helps preserve them. And it's just kind of a pragmatic thing. You know, it just was too expensive to try everything at once. So the cost had to be spread out over a period of 10 years. And in fact, NASA had to actually team up with Europe to be able to afford to do it. So Europe will build the rover that picks up the samples. NASA will build the system that takes that rover to Mars and lands it the way we landed just recently. And NASA will also build a rocket that puts the samples up into orbit around Mars. And the Europeans will build a spaceship that goes to Mars and picks the samples up in Mars orbit and brings them back to Earth.
You really think they could do that?
We came up with this idea in 1972. I've been working on that sort of mission ever since then. In fact, it was our company, Martin Rayette at the time, that came up with the idea of doing it that way by putting the samples into Mars. And then that was adopted by NASA. So yeah, we think it can be done. Yeah.
I'm sorry, I don't mean to be a naysayer or a questioner.
Well, the Europeans say they're going to use artificial intelligence on the rover so that they won't even have to tell it how to pick up the little tubes. The rover will be able to recognize the tube when it sees it, drive in the right orientation, reach down, pick it up, dust it off, and insert it into a little canister to bring the samples back. That'll all be done automatically without humans having to give the commands on how to do it.
Great. When would that launch, probably, or do we know? Would it launch in 10 years?
Well, they were saying 2026, and I think they just said maybe more like 2028. Leonard, you may know better than me.
Well, they did an independent analysis. NASA asked a group to look at that. Dave Thompson ran that study. And I think you're right. I think they thought it was too optimistic for 2026. They're still holding on to, they're hoping to get these samples back by 2031. Is that the date?
It could be. Yeah, that'd be about right.
That. How about for you, Ben? I mean, and Vera, I'm sure you're the same position, really, about, you know, you've been involved with Mars exploration for so long. What was going through your mind when this 7 minutes of terror was going on? Do you ever get used to this, you know, to hold your breath and bite your nails as these things go? How bad was this one?
Well, I must say that I was not nervous at all because I figured out if the mission to asteroid Bennu, which is so tiny, so small, was successful, they were able to, you know, do it so precisely, I figured out Mars is bigger. So the worst thing which can happen is that it lands a little bit off. But then Ben corrected me and he said, oh, this is much more complicated than asteroid Bennu. But the conclusion is I wasn't nervous at all. And I think this is like when people go for some complicated surgery these days, you know, I don't know, hip replacement or whatever, spine surgery, everybody's nervous. And doctors make jokes when they operate because they know it's really okay. That's what I think.
How'd you hold up, Ben?
Good.
How'd you hold up, Ben? Were you okay? Was it all pretty matter of fact?
I've not only been through all these landings, but also all the launches, which are just as nail-biting. So after a while, you just kind of try to little bit ignore it. But I'm a little more uptight right now because today they're trying out this Pixel instrument to make sure it's still working okay. We checked it during the cruise on the way there. It was just fine. But when you land, there's about a 10G acceleration when the aeroshell hits the atmosphere and the parachute comes out. And so if something's going to break, it's probably then. So I'll know for sure that the instrument's working.
That's great. So what is your part of that instrument, Ben? Like what?
Well, it's a technology that I have a lot of expertise in because I developed the original version that flew on Viking, and this is a much more advanced version. So I helped in some of the design choices on how and what to put in it, and I helped on some of the early data analysis. And what I'll be doing during the mission is we'll be taking turns, but we'll be setting down what the commands are to the instrument on how to analyze the sample. And then as the data comes down, we'll be analyzing that data to determine what elements are in the sample.
And what does PIXL stand for, that acronym?
Well, it's a little bit contrived like a lot of them are, but it's Planetary Instrument for X-ray lithochemistry, I think is the name. Actually, I argued against the name because it's easy to confuse with PIXEL, which is the unit of cameras. But anyway, it caught on nicely. But basically what we'll do is we shoot a focused X-ray beam onto the sample and we scan it across and we create an X-ray picture of the minerals in the rocks that we're analyzing. And we can tell you at every little spot what the elements are. So we can actually see individual minerals. This will be the first time we've ever been able to do this on another planet. So it could give some very, very exciting data and will help us decide which samples are most important to bring back to Earth and which ones aren't.
Ben, so far, have we discovered any new elements that don't exist here on Earth that were in some of the Mars rocks?
That's an excellent question, and the answer is no, we haven't. And part of the reason is we think we understand all the elements in the periodic table, and that's all the elements there are in the universe, not just on Mars, but in every star and so forth. But what we didn't know for sure on Mars, would it have some elements much more abundant or less abundant than on Earth? And that turned out partially true and partially not true. So a lot of elements like silicon, about what we thought. We thought we'd have high iron because Mars is red, it's kind of rusty. So that turned out to be true. But the sulfur was a huge surprise, much, much higher than anyone thought. In fact, when we calibrated my instrument on Viking, I was given 25 standards by geologists, including the U.S. Geological Survey, of all the different kinds of rocks we might find on Mars. And not a single one of those 25 rocks had enough sulfur that we could even detect it.
Really?
Yeah.
Is there any possibility of those higher numbers of sulfur, for example, being inimical to life because it's too strong?
Because of what? I missed the last one.
Because there's too much of it.
No, actually, I've worked with a scientific group at Wichita State University, and I'm advising them on what sulfur to use. But they found many organisms which can survive complete saturation of the sulfate salt. They're mostly magnesium sulfate. It's what you buy in the drugstore called Epsom salt. Epsom salt. And so, yeah, true, a lot of life can't survive fully concentrated Epsom salt, but in fact, there are quite a few organisms which can. These are organisms they found in lakes that are very salty.
Ben.
All great questions, by the way. You guys are super.
Yeah, Ben, Clark Chapman here. Good to see you, Ben. Barb earlier asked,
hi, Clark.
Barb asked the question about whether there would be changes in the 10 years from when the samples are collected to when they're brought back. But I have a question about, you'd like samples that haven't changed for billions of years since the lake was there and the possibility of life existed. And of course, over the billions of years, the Martian surface has been turned over with regolith and with being beat up by the solar radiation and so on. So what is the approach to obtaining samples that are least likely to have been changed over billions of years?
Well, it's a good question. You know, on the recent mission, on the Curiosity mission, there was some potassium argon data, and they are claiming ages of only millions of years on some of those samples. And the idea is that these were, because they were taken from a little scarp, a cliff, that had eroded back. And so it had been protected from radiation for a long time. So that's one possibility. We will be drilling, and the drill goes about 8 or 9 centimeters deep. So the deeper you get, the less exposure that sample is gotten. And then we might find samples that are newer. We're not drilling. The European rover is going to drill down 1 or 2 meters. So that's something we'd like to do someday.
Yeah.
Because you might find material that's been protected more. But I think you make a good point, and I think I'll keep that in mind as people are arguing about what samples to take, that's something not to consider. By the way, I just want to say publicly with everybody listening, I want to thank Clark Chapman again, because Clark had a student working for him named Bo Bierhaus, and I was looking for someone to succeed me at Lockheed Martin. And Clark told me when I had my little sign-ups and I was looking for something, he says, I got just the guy for you. And he was right. And we hired Bo, and he's still involved very deeply, very involved in the OSIRIS-REx mission right now. So thanks, Clark.
Sure.
Ben, you might want to mention, Ben, maybe mention a little bit about what you think. The helicopter got a lot of press. It continues to get a lot of press, but I'm very interested in the MOXIE experiment. You might want to just mention that and what expectations people have for the MOXIE experiment.
So MOXIE is a technology demonstration, not a scientific instrument. And what it'll do is try to make oxygen from the carbon dioxide in the atmosphere. And the reason that might be important someday is when humans are on Mars, especially if they're going to spend a long time there, they would be able to make oxygen for breathing and also for making a part of the rocket propellant that they would need to get back up into orbit and come back to Earth. So it's kind of a long range objective, but it's the first time we're actually trying to do something like that on Mars to demonstrate that we should be able to do something like that. So MOXIE and the helicopter are, like you say, going to get a lot of attention, but those are not the scientific experiments of the mission.
I'll point out that the way it's going to make the oxygen is very different from the way Robert Zimmer's approach was of the SOD88 reaction to actually create methane and oxygen.
Yeah, there's several ways to do this. Yeah, true. Yeah. There was a competition, and in fact, Lockheed Martin was teamed with, I think, Johnson Space Center and their proposal was not selected. Moxie was a former JPLer, and this for some reason this rover is just loaded with JPL instruments. I don't think that had anything to do with the selection, but at any rate, he had been working on that concept, you know, in parallel with other people working on other concepts. But I think the important thing is to show that something you develop in the lab and test in the lab simulating Mars conditions actually works on Mars will go a long way in convincing the engineers that you can take some of these things seriously in the future. I mean, some astronauts have said, I'm not going to Mars unless I've already got enough oxygen to get back home.
Ben, hi. What is your favorite experiment on this project?
Well, of course it's Pixel because that's the one I'm most involved in. But I was actually involved on Curiosity with what's called their ChemCam, but on this mission, an improved version is called SuperCam. So I've worked closely with those people as well. And you know, all the instruments are more sophisticated than things we've ever flown before. So they're all going to be interesting. There's going to be a ground penetrating radar trying to detect ice beneath the surface. The camera now has a zoom capability it didn't have before. There's going to be what's called Raman spectrometer, which is a way to look for organic material. It's also mounted on the arm. And let's see, well, there's weather station. So there's other instruments I wish could have flown. So,
oh yeah,
you know,
what are those? What are those? The instruments you wish could have flown?
Well, I would have liked to have seen a follow-on to the instrument called SAM that we have on Curiosity, which does wet chemistry and really can detect these organics down at the parts per billion level. And they have an advanced version, which is going to fly on the European rover, but not selected for some reason for this mission.
Might want to mention the kind of another media hype that we're all going to give it is listening with these microphones. Yeah. And I gather on the on that laser system, it might be able to hear the laser shots going off with the microphone, I gather.
Yeah, you're right. We might be able to hear them. They make a little ping when they hit. The laser, when the laser hit, it essentially vaporizes the rock. It makes a little hole in the rock. And we can see those holes, so we can see exactly where it hit. And that's good when you're looking for veins and stuff. But also the Moxie has a pump, and the pump makes a lot of noise apparently, and so they're hoping they'll be able to hear that. It's hard to hear things on Mars because the atmospheric pressure is 200 times lower, and you need gas to transmit acoustic waves. So, you know, if you're in space, you can't really hear anything because it's vacuum. But on Mars, we'll be able to hear a little bit. So it's just an experiment to see what we might hear, plus some of the noises of landing and stuff.
And I gather they can use that sound. What I really liked about it, frankly, is that it could be a diagnostic tool. You might be able to hear that pump going out of whack. You might be able to hear some other parts of the rover creaking around, maybe get an early warning something's going on wrong.
Yeah, right. Yeah, the pump experts claim they can tell by the pitch of the pump whether it's working properly or not.
Okay.
And what's wrong with it.
Yeah.
And that was Kelly McMillan who was asking that question, who you know well.
Oh yeah, hi Kelly.
And I just wanted to mention she posted a number of links and explanations on the chat there that I guess people could access later too. But on the case for Mars.
Carter Emmart, I gave a bunch of the Case for Mars videos to Carter to transfer over into video format, online format. I got one from him this week that was from 1981. It had you, Tom Meyer, Chris McKay discussing the atmosphere of Mars. And it's just fabulous, Ben. You were in the audience, Tom was speaking, and Chris was moderating, and it's fabulous. So I just got that this week, the day before the landing.
Oh, great. Yeah, I got in touch with Carter last fall because Vera was on a panel discussion with Neil deGrasse Tyson. And I wasn't sure if Carter was still there at the museum, but we got in contact through one of the people that was working with Vera at that talk. Her talk was about alien life in the universe.
It was very interesting.
It sounds interesting, Vera. Do you
it's
have
on
a link?
YouTube. It's on YouTube and it's had 80,000 views.
Wow. Do you have a link to that, Vera? You can put it in the chat room here.
Or what would we search for? Or just search for your name.
Yeah.
Okay.
Okay. And we could put
Thank you. Nice to see you, Ben.
Nice to see you.
Yeah, some of these people were mentioning were all part of the Case for Mars conferences, which started in the 70s, right?
We started organizing in the 70s.
It was every 3 years, and it was making a case for going back to Mars. And it was about 20 years or so that it took to get back to Mars.
We had the first Case for Mars meeting, and it was just, I think, just as the shuttle was starting to operate. We were all excited, we're definitely going to Mars now, the shuttle's working. We had, I think, 75 or 80 people at the first Case for Mars, because some of the people from JPL were very confused. They thought it could be a Star Trek conference, but they weren't sure.
Now, those were all held at CU.
Yeah, at University of Colorado.
And that was the Mars Underground. It had to be underground because NASA had a moratorium against all its employees that were not allowed to talk about Mars missions for about, 15 years.
They didn't want to talk about it. And then the Case for Mars kind of, I guess, evolved into the Mars Society, Robert Zubrans, and Dewey, who's on there, has given us some talks about the Mars suits and the Mars Desert Research Station. And he and John and Mark, I think, John and Mark on here go to a lot of those Mars meetings, right? The local Mars group meetings. Yeah.
Ben, last thing for me, and I'll shut up. I'm so fascinated by this Mars topic. I mean, let's move it out a little bit. I mean, return sample. There's been a lot of other ideas about lower costing missions to Mars. Bruce Jakowski did a study that NASA kind of blew off on low cost landers and even orbiters that can do more for less money than a return sample mission, which is going to be pretty pricey. What's your view of how do we proceed, beyond return sample? Because, Mars is so diverse, so magical. Return sample is not going to tell us everything about Mars we may want to know. What's your take on the future?
Well, what I've thought for quite a long time is that these higher class rovers with the RTGs and Curiosity, Perseverance, they're so darn expensive. I mean, Perseverance is a quote copy of Curiosity, and yet it costs a couple of billion. So what I think we can do now is have a fleet of small, cheaper rovers And I would, you know, allow all kinds of people build these, industry and universities and stuff, and find ways to get them down on the surface cheaply and let them roam like crazy, but having the capability to look for the kind of the killer samples, find something really organic rich, hopefully. And later, then you go to those locations and pick up those samples. But we can row much faster on Mars if we have more of a communication infrastructure, and we have rovers that are very limited in what their capabilities are, but they're very targeted towards trying to make these major discoveries. And once you make a major discovery, then you can spend whatever it's going to take to go get the samples.
Yeah. What if something comes along in those 10 years that makes those samples totally obsolete? Like a Chinese man walking on it or something?
Well, as Clark Chapman pointed out, these samples have been sitting around for some of them a couple of billion years. And so if they still have organics in them, it won't be a problem in a few years to pick them up.
Yeah. But and the Chinese, are they thinking about a sample?
Yeah, the Chinese, I mean, they're going to do, I mean, they're one of their ambitions, and they kind of showed their stuff with the lunar sample return, is to mimic that for Mars. And we'll see how well they do on this, you know, this lander coming up in May, June, but they're very anxious to do a return sample mission for Mars as well. So we'll see. Yeah, and hopefully they'll share the samples. We'll have samples to share with them, so I'm sure they'll be able to bargain. Unfortunately, their whole program is always shrouded in mystery until something happens, and so we're not even sure how well they're doing planetary protection. Okay, go ahead.
Yeah, I was just going to ask, are they obeying planetary protection?
Vera, can you speak a little louder?
I was saying that unless they implement all the planetary protection recommendations and have clean vehicles, they may contaminate Mars. So we'll find, you know, for Mars that we brought up from Earth. So that's what I'm personally worried about.
Yeah. We're really concerned about that too. So anyone else have any questions or comments?
I have a question on the contamination. If all the minerals and chemicals that have been found are the same as those on Earth, why would there be any contamination?
Contamination would be basically with remnant of earthly life, which means organic chemicals which are part of life. And if we bring those to Mars, or even if we bring bacteria and stuff like that to Mars, then we would create what we would like to be biosignatures, meaning signatures of life, but instead of being biosignature of life on Mars, they would be biosignatures of life on the Earth.
So I probably created the wrong impression when I said that we have the elements, the same elements on both planets, but those are only elements, not the molecules. And so the organic materials are molecules that are not on Mars that we've discovered yet. Yet we hope they are eventually to find that are similar to life.
So just one clarification. When we talk about elements like Ben was talking about iron or copper or vanadium, organic molecules will be things like sugars or proteins. Haven't found sugars or proteins on Mars yet. But if we bring contaminants from the earth, material on earth which is alive or which was alive in a reasonable past will have these molecules. And when you deposit them on Mars, then you contaminate them.
Even a fingerprint is too much organics.
With the conditions on Mars being so inhospitable to life now, would there be any growth of any organics that we would happen to take there, or would they just be left where they're left?
Well, if we created liquid water on Mars and we weren't biologically clean, and we go to a lot of trouble to be clean, if we weren't, and we created water and the right organism got in that, it probably be just fine.
Yeah.
And the way we can create water is we heat the soil and the ice turns to liquid. And one of the things we've worried about is crack, and this nuclear battery got buried beneath the soil. It could create a little zone that would be a little puddle and contaminate badly.
Yeah.
The spacecraft that crashed on Mars, which one was that? The
Schiaparelli.
Yeah, Schiaparelli. Did that have? Would that have to be a nuclear RTG battery, or could it be just, well, something that stores the solar panels, a battery, the solar energy?
What mission are you talking about?
We've had a number of crashes.
Yeah. Would any of the crashes depend on whether it was a nuclear-based battery or?
Well, there hasn't been any crashes of vehicles that had nuclear capability. Yeah. So Vikings, the two Vikings had it, and these two rovers have it. They've all landed safely.
So the other ones that had solar panels and must have had some kind of batteries, right?
Those are not a problem so much because the solar panels wouldn't generate, they would be broken up or burnt up. And so they wouldn't cause any heating.
Oh, right.
They wouldn't be operating.
So
another question on the contamination issue. I've read about terraforming other planets. Wouldn't terraforming be a contamination?
Yes. The ultimate.
Big time.
Well,
yeah, that's the argument against it. Now it turns out terraforming probably doesn't work anyway. Probably not enough carbon dioxide there. But if you could, and if you did try to do it, you would irreversibly contaminate the planet. So that's why most scientists don't really want to do it.
And yet, why are we going there if it is not for the human race to have a way of living elsewhere?
Well, if we really need to go to live somewhere else, we could go live on the moon. It doesn't have all the same resources, but it's 100 times easier to get to and from than Mars. So it's not as if we don't have anywhere to go. And the much more important issue, I think, to the human race is what, how did life start in the first place? Why are we even here? And can it start at other places? Is there more life in the universe? And if we have to go to another planet to survive, we must have really messed up here. Why wouldn't we just mess up again if we did? So,
I would just like to add something for everybody to think about. In about 1991, when I was working with Leslie Orville and Stanley Miller, we had a big discussion about should we send bacteria on Mars, or should we keep Mars clean from all Earth? contamination. And I remember I was new, I just arrived, and I said, sure, let's send bacteria to Mars, have evolution start on Mars, because if we are doomed on the Earth, at least something will live on Mars. They almost threw me out. It was a pretty bad thing that I said. However, this is totally unapproved opinion, but I think that life is so wonderful that even living bacteria is a miracle. So if we cannot save ourselves, if we're gonna ruin the earth completely and, you know, kill all the life on the earth, it would be nice for little bacteria to survive some. Okay, Ben is not gonna talk to me at all now.
John, I think you had a question, didn't you?
Yeah. Can you hear me?
Yeah.
Oh, good. My screen didn't light up. You know, there's a way to at least inventory what you're sending there by swabbing the surfaces of the lander to see, and then culturing and identifying what bacteria are there. Did you know if they actually did something like that?
Oh, yeah.
Or any of the rovers?
Yes, you're right. And we did exactly that, starting with Viking. And actually, I was very much involved with one of our later series of landers, the first new land after Viking, and helped set up a lab that did that. So we clean everything, and then we swab, and then we go culture in the little laboratory. And we look for, what we look for are heat resist, well, spores, but they're heat resistant because ordinary bacteria can easily be killed. But if you had spores on the lander and then they got to Mars and turned back into bacteria, then they would be able to survive the trip. So we go to great extremes to keep these things pretty clean. They're not, we don't call them sterile. They're not like 100%, but they're extremely clean compared to our normal surroundings.
Then I guess that begs a question. We don't know if China, for instance, is doing the same.
Well, about China and any other country for that matter who does not obey these international rules, the problem is, in this regard, what I said a moment ago, we all have to make sure that we don't contaminate planets or other objects which we think may have still life. There may be some life underground in Mars. And also planetary protection also protects planets where there is so-called chemical evolution. If you can get organic chemistry going, that is a good potential for life. So we don't want to contaminate these objects either, because then we won't learn. Is chemical evolution meaning these organic chemicals reacting and eventually leading life? Is this possible on this planet? That's why we must all agree not to contaminate anything, not to further notice. That's what it is. And I'm not sure that Chinese would obey this necessarily, at least in their own culture. And I had even colleagues in chemistry who don't believe in patent protection. They believe ideas are free. So if you spend 10 years developing something, tough luck. You know, they're just gonna take it and they don't think anything about it. So this is what I'm worried about, the cultural differences that are gonna come into play, and maybe, you know, they're gonna contaminate Mars.
Okay, well, I know it's a little later where Ben and Vera are there an hour later. Anyway, we don't want to keep you up past your bedtime. But if there aren't any other questions, or if there is, you know, I mean, we can keep going if you want here. I just wanted to point out a couple things. One is that Mars is very high in the southern sky. It was near the moon very near the moon on the night that the rover landed. But yeah, go take a look if you haven't. You know, it's orangish and pretty easy to see just naked eye. Binoculars are good, a telescope too. And also, Ben, I wondered what's the significance of what's on your hat? What does that say, Dork Horse?
I'll let Vera explain.
Well, we looked for Ben's red cap, which has OSIRIS-REx mission, and he has another one with the NASA mission, and we couldn't find it. So we figured out this blue hat goes well with his blue suit. And this is Door County, Wisconsin, that we both visited, and you know, has no special meaning. But Ben likes
I wasn't sure if it had some kind of Mars meaning there too.
It's
really.
Water on Mars.
Water on Mars, right? Blue. Great. Okay, well, so anyone else? I mean, sometimes we stay on here longer, a bunch of us chatting. They're about, I did want to mention there were, or are, 41 of us on here tonight, which is a lot for our group. And I also wanted to say for the people who are new, I see a few people who were here for our UFO meeting last time. Larry Lemke was one of our speakers for that, Ben, who you know, Carol Stoker's husband. Yeah, just, I don't know if Ben and Vera, if you want to stay on, a lot of times we stay on later and talk among ourselves. But, and anyone else want to ask another question or comments?
I just want to thank Ben and Vera. They were fantastic.
Yeah, yeah, really. Yeah, let's,
thank you.
You unmute yourself and clap. Thank you so much. We truly appreciate it. Yeah.
Okay, we enjoyed it too.
Good. Yeah. Awesome. Great. So you're going to go? Okay. Thank you so much. We truly appreciate it. Let us know when your book is available at the price you mentioned, or that you said it's going to be cheaper. Wait. And then when we can all be back when you're in Denver and we can all be back up here together, yeah, bring some of your books. And our group is pretty interested in buying books and getting them signed by the speakers. So we'd love to have that.
Okay, we both had our first shot and we'll be getting the second shot soon. So we'll be coming back to Colorado for the summer. Good.
Okay. We'll hope that we'll be back meeting in person sometime this summer. Yeah. Okay. Thanks so much.
Take care.
Okay.
Thanks, Ben.
Yeah.
Yeah. Thanks so much. Really. And then, yeah, anybody else who wants to stay on? I'm trying to get this back to our, oh, there we go.
Did John Williams